Welcome everyone to the June 2023 meeting of Mornington Peninsula Astronomical Society. Maybe that's a little bit loud, I'll turn it down a bit. Out there. Yeah, sounds about right. What we have up there on the centre at the top there is the recent test of the new rocket dying engine for the NASA Artemis 5. So in other words, this won't fly until the 5th Artemis mission. So the next one to go in about a year or so's time will be the 2nd Artemis mission, so it's still a little way off, but this was a full test of it. What you see at the bottom there is all the water deluge system blowing out steam from the exhaust, something which Elon Musk didn't quite remember to do for his recent liftoff, whereas NASA indeed did with theirs. And this will go for a few minutes in the background as they tested it successfully. The top right there we see an image taken from the movie Star Wars. I believe it was Luke Skywalker's planet, was it Tatooine, which is in orbit around a binary star, so not a single star like ours. As shown in that image there, 2 stars, and one of these has actually been found by a Monash University astronomer, Rosemary Marbling. She was actually due to give us a talk just at the time when COVID hit, and so we managed to get a recording of her talk a few years ago, which you can find on YouTube. But she's now a co-discoverer of one of these so-called circumbinary planets. In other words, a planet around 2 stars, in orbit around 2 stars. And in fact, in this particular case, it was 2 planets in orbit around 2 stars, which is unusual because that's the second example of that has only ever been found. So it's done really well. Down the bottom of the screen there, in the last month, has been announced some pristine samples of Earth's mantle have been taken, and shown there on the middle right is the ship Joyous Resolution, which went out to the Mid-Atlantic Rift, which, the right button, down here, it positioned itself in the middle there at Atlantis Massive, which is a bit like an underwater mountain, and drilled through, and by really good fortune they were able to drill very, very easily through the crust at that particular position. Really young rocks there, only about 10 million years old apparently in the paper, and they were able to drill down to about just over 1 kilometre through the mantle, so they've been able to bring up to the surface parts of Earth's mantle pretty much unchanged. Now some of the rocks, as they brought them up, were impacted by the salt water, but they're pretty confident that they got a good sample. Now it took that ship a month of drilling to actually drill that far down into the mantle. Normally on land the mantle can be tens of kilometres thick. I don't know if you recall, but many years ago now, the Russians tried to drill on land down to the mantle. They got to about 12 to 12.5 kilometres, I think, down, and they were well short of going that far before they ran into technical difficulties. The crew of the ship here was actually anticipating drilling technical difficulties as well, but it was almost a perfect sample that came back up, and they had no trouble whatsoever. For the first time, a bit of the mantle layer had come up. One of the surprises immediately was that the difference between Earth's crust and the mantle underneath it is not sharp. So they described it as interlayered, so you can think of it as like fingers interlaying like that, where it's like a gradual transition between the two. And those familiar with nickel-iron meteorites from asteroids would be familiar how when you go from the transition zone between the core of the asteroid and its outer layers, that you'll get these meteorites that are actually mixtures of the two during the transition zone. So it's not a very sharp delineated boundary, rather it's a gradual one. Now we'll close that rocket off now. There we go. Welcome tonight. If this is your first time to the Mornington Peninsula Astronomical Society, and if you are new and a new member, feel free to say hello to Nerida. You'll see what Nerida looks like because she'll be up talking in a little while later today. I'll go through as usual events of the past month and the coming month. Then I'll throw over to Andrew Campbell to speak about the Australian Photographic Prize, and also maybe give away some astrophotography secrets as well. Then on to Chris for monthly photo challenge, and Nerida will talk about her adventure down to Buchan. There's no sky for the month this month, so we don't have anything to show there. Then we'll break for a bit of a tea break, and then following that we'll look into the physics of colour and the psychology of colour as well. And that covers things like even branding and why people buy things the colour that they are. And then towards the end there, we'll look at everything to do with rainbows, how they form, the different types of rainbows and halos that you can get. And then at the end, we'll close with Kilauea erupting a few weeks ago, and you'll see the start of that eruption as well on the Hawaiian island. So beginning with the recent events, and there's Nerida looking at the daytime sky through the dome outside, and amazing filters they can use on cameras these days to pick up the stars in daytime. Look, you can see all the stars there. And very nice composite there. And that was the front page of Peninsular Essence, which is published across all of the Mornington Peninsula. Now, 24th of May, committee met by Zoom, and we obviously discussed a bit about that article. We've applied for a defibrillator grant. There is a defibrillator actually next door. And we got a thumbs down on the defibrillator. Okay, we didn't get a defibrillator grant, but then by the sound of it. And we also talked about the forward planning coming forward, because we've got a fair amount of big events between now and the end of the year. 26th May, a couple of days later, we had the Sorrento Scouts up here as part of our Scouts, Cubs and Guides night. We had 30 attend, but unfortunately it was 100% cloud, but nevertheless, Catherine and I gave the talk and answered their many hundreds of questions during the evening. 2nd of June, Trevor gave the talk at the public night here and had a good turnout up to our sort of limit at this stage. Very cloudy, but nevertheless those that stuck around were able to see something. Oops. Now coming up, over on the right-hand side there, you'll see the first one this weekend, I believe it was, a collaborative public night at, in conjunction with us, the ASV and the Latrobe Valley Astronomical Society, out at Locksport, going off to see the Aurora Borealis, as advertised there in the newspaper. So obviously it's not Locksport in Victoria, but it's Locksport in Scotland, I imagine. So they're going to be travelling a long way this week to see the Aurora Borealis at the best of times. On the weekend also here, there'll be the usual working bee and barbecue at the Briars. Next committee meeting will be next Tuesday, so a slight change next week. For those who've booked, the Neil deGrasse Tyson talk up at the Melbourne Convention Centre is coming up on the 6th of July, so not far away now. We've got 12 in the group booked, and I believe anyone who wishes to book directly themselves is actually eligible for a 20% discount. Now that won't be through us, you'll be seated somewhere else in the audience, but the organisers have actually now offered Astronomical Societies 20% off to book tickets. So obviously they haven't sold as many as what they might have been hoping. 7th of July, the next public stargazing night will be here at the Briars again. We're fully booked out for that one at the moment. Still to work out who's going to be talking at that one. Then we've got a retirement home visit by Manfred. I think that one is still going ahead, although I haven't confirmed it with Manfred. Cosmology group will meet here on Saturday the 15th, as usual. On the 19th of July will be the next meeting, which will be the annual general meeting of the Society. So that means that you'll receive a notification in the coming days that the next meeting is the annual general meeting. And that means if you have aspirations of coming onto committee, you can nominate by the due deadline and get that into the secretary beforehand, before the AGM. And down the bottom there, the three big events between now and the end of the year. We've got the Astrophotography workshop on again this year. It's about half booked out at the moment with our capacity, so very, very strong booking level, given that we're still some months away from that. Then the Telescope Learning Day at the Briars, so the second Telescope Learning Day, 21st of October. We haven't opened bookings yet, as far as I know. And Vastrop, we haven't opened bookings yet as well. So tonight's visitor is Andrew Campbell, sitting at the front here, who's a multi-award-winning professional photographer. So he does this as a job. I'm very impressed by some of the titles here. Grand Master of the Australian Institute of Professional Photographers, a Fellow of the New Zealand Institute of Professional Photography, and a Master Photographer of the WPPI. I think that is that Wedding and Portraits? Yeah, in the USA. Also looking at his bio, he's won the David Malin Award for Astrophotography himself in 2015 in the Deep Sky category. Several years he's been highly commended and honourable mention. He's also been the Australian and Victorian Science Photographer of the Year for 3 years by the Australian Institute of Professional Photographers, when that still existed. He's had images on NASA's Astronomy Picture of the Day 6 times, so quite a few times. He judges at state and national levels and awards while the AIP existed, and he'd done that for about 25 years. He's exhibited his work, some may have heard of the Ballarat International Photo Biennale. They've had a couple up there, I think, and he was at the 2015. And also he was a finalist in the National Portrait Prize as well. He also speaks on astrophotography and has spoken at the World Science Festival in Brisbane, and as well as a number of astronomical societies, such as ourselves. And including virtual talks as well to overseas. And with that, I'll ask Andrew to come up.
Thanks for that very warm welcome, and thank you guys for having me here. This is my first time at the Mornington Peninsula Astronomical Society because I'm a Melburnian, and it's lovely. I'm really impressed. It's a fantastic facility, and really thanking you lovely people for coming along tonight. So, who's an astrophotographer here? Ooh, there are a few. Don't be shy. It's all good. Excellent. So what I wanted to talk to you about tonight was a new initiative, and that's the Australian Photographic Prize. This was a venture that came out of the collapse of the Australian Institute of Professional Photography, which folded during COVID. And my wife, Robin, was heavily involved in that as the chairman of jurors of the national photography competition that they ran. After about 3 years of being in the dark and loneliness and only connecting via Zoom, it was decided that with her business partner that she would create something out of the ashes of that, which became the Australian Photographic Prize. That ran last year, had 700 entries. It was for professional photographers and amateur photographers in all the genres that you could imagine: landscapes, weddings, portraits, etc., etc. This year, though, she said, "Honey, you can't enter. But what do you think about opening it up to astrophotographers?" And I thought, well, that's a fantastic idea. And she said, "Great, because you can't enter, but you can basically organise it." So, okay, no problem. What makes this competition different to any other astrophotography competition worldwide is the fact that anyone who enters can get written feedback on their entries. And that's something that's gold. Because if you enter any other competition, you'll get nothing. If you enter the David Malan Awards and you're successful to be a finalist and you go all the way to Parkes, your images may get a brief mention by David, but that's it. If you get involved with the Royal Photographic Society, the one that's run out of Greenwich in England, you enter and you get nothing back at all. But this one, first up, you're going to get feedback. You're going to know where you stand. You're going to get a sense of, where you are. We do this photography thing, astrophotography in isolation. So it's nice that you can actually get, genuine feedback from experts. Now, in addition to that, the top 25 of each category, and I'll get to the categories in a minute, those are going to be judged live. And when I say live, there's going to be 5 judges sitting in a room debating each of those images publicly and broadcast on YouTube. So it's totally transparent. Just imagine how exciting it'll be if one of your images is one of those 25. Cool. And the debates, and that's what makes this particular competition process so exciting, are so educational. Because what will happen is an image will come up, the judges all have to give it a score out of 100. The panel chairman, which is going to be me in this case, will announce that score, and let's say it gets 82. And then someone will put their hand up and say, no, this is worth much more than that. This is worth 95. It's the best version of the Helix Nebula I've ever seen, blah, blah, blah. And then the debate will happen because someone will go, well, no, I mean, it's sharp, but, the stars aren't round or whatever. And this debate will then go on for a little while until the judges then have to rescore. And the person who put their hand up first can't change their score. So they have to be a good debater if they want to sway that panel to get them along with them. Anyway, whoever eventually gets the highest score wins a telescope. A very nice little William Optics Red Cat. And in fact, there are 2 of them to be won. So let's see if I can press the right button here. Ooh, it works, great. These are your judges. You may recognise some of these names. We've got Dr. Tanya Hill coming from the planetarium. She's an actual astrophysicist. So her work was in black holes. I think she discovered 6 of them. Anyone who's been on something called Ice in Space might recognise strongman Mike Sidonio's name. A bit of a feather in our cap to get Mike down. He's highly regarded as one of Australia's very best astrophotographers. And he's recently built an observatory on top of a mountain outside of Canberra. It's the highest privately owned observatory in the country. So Mike's dedicated himself to, living up there, and somehow persuaded his wife that it was a good idea that they live up there. Marcel is from Germany. Marcel is highly qualified, works with Xavier Strotner, and they they find stuff. And they have found 350 planetary nebulas that didn't exist as far as the charts went previously. So pretty amazing that people can actually still discover stuff, even though we know space is effectively Google mapped, and you can use your Sky Safari or whatever your favourite app is to look up and find things. But there is still amazing stuff up there that hasn't been found. But this guy he specialises in finding them. For those of you who shoot wide field, as in what we call terrestrial foreground with the Milky Way, you've got Ari Rex from Canberra, who's a specialist in that particular genre, runs workshops in Canberra. He's very, very good. Diego, you may have heard of. He builds fantastic telescopes. And he's a really nice guy. And this other lot down here, well, don't worry about them. No, it's all good. There's some talented photographers there as well. This is the astro landscape category. So this is the kind of thing that I was talking about, where you would see a Milky Way and a terrestrial foreground. That may also include such things as star trails, those funky ones where you do the time exposure at the south celestial pole and you see the trails. It includes the auroras, be they northern or southern. Basically anything you can imagine that looks good. There's a couple of conditions there. You can put in a composite image, but it must be taken at the same location. So if you shoot that amazing sky and that amazing foreground at different times of the day, that's fine. But don't go shooting this fantastic Milky Way at Uluru and then a really good landscape here at Mornington and think you can put them together. Sorry, guys. Okay. This is the deep space category, what you would classically assume for telescope work. That's some images there from Mike and myself and Diego. And you can enter anything that you've created after June 2018. So dig into the archives, see what you can find. That said, we've put a limit on using data that you've sourced from subscriptions. So if you haven't actually captured the imagery with your own gear, with your own scope, and you've just gone and downloaded some data from Deep Sky West or Chiliscope, sorry, that's not fair on everyone else. So it's got to be your stuff. Cool. There's a question that always pops up, and I'll get to it straight away, about AI. Use of AI is permitted sparingly. So we're all aware that Russ Croman has Blur Exterminator, Star Exterminator, Noise Exterminator, Topaz exists. All those sorts of apps are there to help you refine and process your images and make them even better. All we're saying is be careful that you're not generating data that doesn't exist. So if you've got a picture of the Lagoon Nebula and the detail is better than the Hubble, and you've taken it with an 80mm refractor on a Skywatcher EQ6 in your backyard, we'll probably ask questions. All right? So we want it to be real. That's all. Okay. Why would you enter this competition? Well, apart from getting the feedback that I just mentioned earlier, this is kind of an opportunity to test yourself. It's a chance to see where you are with your photography, get the feedback, get educated a little bit about where to go to the next level, and then get involved in the actual judging itself. I'd encourage you to come to the judging. It's very exciting. Now, the judging itself is on Friday the 21st of July, Photography Studies College in Melbourne. And yes, there's a very expensive price of entry of $10. So that will get you in for the whole day if you wish, because you can see the other categories being judged as well, that sort of more terrestrial photography as well as the astro stuff. But we've allowed 3 hours for the astro judging, and it'll be very educational and it'll be fun. Okay. You also get funky badges if you're a finalist. So the little badges down the bottom there that you can put on your work. Kind of cute. Those are the rules. You can download those anytime. The website is current and live. The entries close at midnight on the 3rd of July, so about just under 2 weeks from now. And if you're anything like most photographers, you'll leave it until the 2nd of July to start thinking about your entry. It'll probably crash the system if you do, but that's okay. And it's part of a workshop and photography event that's happening that whole weekend. So Friday is Astro Day. You'll also see there's speakers there who'll be presenting on not only astrophotography, but other genres of professional photography. You're most welcome to come along and see that. That's all included in the $10. You have to pay the $10 because you have to register, because it's a college. So they want to know who's coming in and going. So if you want to come along to the judging, you have to buy a ticket. You buy it online, and you should do that sooner than later. All right? But wait, there's more. Mike, we've persuaded him, Strongman Mike, to stay on for the actual presentation of the awards, which will happen immediately after the judging. And as part of that presentation, he's going to give a presentation himself on what he has done. Among other things, he's discovered a galaxy, and he's going to talk about his work. And for $75, not only will you get to hear Mike speak, but you'll also get all you can eat, all you can drink, catered for you. And that includes beer, wine, soft drink, non-alcoholic beverages, a 4-meter long grazing platter, etc., etc. So that's all included in the $75 as well. Cool. And there's your links for that. All right. Any questions about the event or the award or the process or any of that stuff? Okay, you're all very quiet. If you would like some help with your astrophotography, and yes, I'm sorry, commercial plug coming up now, I have spent the last 2 years-ish during lockdown and afterwards documenting all of my processing techniques using Photoshop. So if you have AstroPixel Processor or PixInsight or Deep Sky Stacker or anything, and you can create calibrated files, stack them if you like, this will help you process those images and get the most out of them after that. So it's taking your data and creating nice images. Currently on special, you can download that now, and it's on special until the 3rd of July. So that's the end of the commercial plug. There's 41 pages in there. They tell me it's good value. Okay, so on to the good stuff. Secrets. Talk a little bit about photography, if we can, in terms of not so much what astrophotographers always do, but perhaps what astrophotographers maybe sometimes don't do. And specifically, we all know we all have to do this stuff, and we have to get this right to get our photographs looking good, all right? Preaching to the converted here, you guys all know this. But maybe some of this stuff is the bit that gets missed a little bit because we're so bogged down in the technical side of getting a great image that maybe sometimes we miss out a little bit on the fact that at the end of the day, we're taking a photograph. And the photograph should have some of these factors. So it should have impact. A photograph should have something that sort of stops you in your tracks. It should have some reason. For example, if you're a judge, you might want to get up and see that because, wow, that's a really cool shot. And I think you'd agree all of those pictures have some impact. Incidentally, did anyone here go out to the eclipse out at Western Australia? Did you get some good shots? Fantastic. Experience of a lifetime. Have you done that before?
2 times before.
Oh, you're an eclipse chaser. You're one of those. Fantastic. I think I'm just going to have to wait until the Sydney one comes up. It's a little bit more convenient, but that sounds amazing. Well done. Did you get some good shots?
Yeah.
You can enter them. A picture should have emotion. It should have something that gets you, as my son would say, right in the feels. So these pictures are by Mark G from New Zealand, and he won the Royal International Astronomy Photography of the Year, I think 2014. But that picture on the left with the family, you know, everyone can sort of relate to it in a way of seeing the majesty of space. And space is there for everyone. It doesn't matter where you are on Earth, what you believe in, or what country you're in. The moment you sort of step outside on a wonderful night like this and step away from the campfire and look up, you ask yourself those big questions. And perhaps that stirs a little bit of emotion in you. And I think that picture captures that. And the one on the right's magnificent, seeing that moonrise. I believe he shot that with a 600mm lens and about 4 months of planning. So, pretty cool. A picture should have a story. And in this case, this is an image that I took of a subject that is quite familiar with the Lagoon Nebula and the Trifid. But I kind of used the narrowband colour palette to pick up a little bit on Van Gogh's famous Sunflowers painting. And by orientating it in this particular way, it kind of picked up a little bit on the idea that, well, maybe there's some flowers in a vase if you stretch your imagination a little bit. Anyway, the NASA guys liked it, and they published it as a APOD, and I think it got 2.5 million hits that day, and I think 1,600 shares on Facebook and goodness knows what else. And that's the amazing thing about APOD, is that anyone can get one because they can draw images from the Cassini, from the Hubble, from the Webb, from all the greatest observatories around the world. And occasionally, some guy in his backyard in Mornington Peninsula can get their photographs exposed to the world. So anyone can submit to NASA for the astronomy photo of the day, And I'm not sure what their selection procedure is because I keep putting them in and they've ignored me for about 1.5 years now. But that one got up, so that was cool. Pareidolia. I do tend to bang on about this. Have you ever cast your mind back to when you were a child? Lie back on the grass, look up at the sky, see the clouds, start seeing shapes in those clouds. Oh, I see a bunny rabbit. Oh, I see Roadrunner. Same thing happens when we look at nebulas and wacky phenomena in space. Our mind wants to make sense out of what it's seeing. And so yes, the Helix Nebula can look perhaps like an eye. The Horsehead Nebula, that one taken by Steve Moore, one of your members here, actually looks like what it's called, but very few things do. And this one on the far right, they call that one the Wolf Nebula. Can you see the wolf in there? Yes. Pretty cool. Now that's just backlit by a bunch of ionized hydrogen. And it's just a bunch of cosmic dust that vaguely resembles the shape of a wolf. Pretty cool. But again, it's that curiosity thing where people will look at a picture and go, oh, that reminds me of something. And all of these little subtle things help the pictures get that attention of the judges or the viewer, and in a competition sense, those few extra points. Composition. We slave hard in this world of astrophotography to get our optics perfect. And our optics are usually most perfect in the middle because that's where the light is ultimately focused. And so if our field is flat and our optics are perfect, then, ideally the most sharp, best bit of resolution is going to be right in the center, which is all very well. But it makes boring compositions. It's not the most ideal thing necessarily to just pop your Trifid Nebula, in this case, right in the middle of the frame, because the one on the right here is sort of obeying something a bit more of what's called the rule of thirds, and it's balanced a little bit. And you can see not only M20 but also is it 21, the little star cluster up on the right hand side from memory, which gives it a little bit of context. Here's some more, same thing. Just because you can fit two objects in the frame doesn't necessarily mean that you should. Because what happens sometimes is we look at the Cat's Paw Nebula on the left, and then our eye scans over to the Lobster Nebula on the right, and then it goes back to the Cat's Paw, and then it goes back to the Lobster, and then it gets confused, and it just sits in the middle, and it rests right in the middle of that dead space. And there's nothing happening in that middle dead space. So the question there is, oh, look, I can fit the Eagle Nebula and the, what's one next to it? M17, it'll come to me in a minute. That one. Just because I can fit them in the same frame doesn't mean that you should, all right? If you're entering it in a competition. If you're doing it for yourself, it doesn't matter. That's the rule of thirds I was talking about. So in a perfect world, whatever you want to look at needs to be on one of these third lines. So it should ultimately reside there because that's where our eyes tend to work with composition. So have a little think about that when you're framing something up. And if you're using any of these programs now, like the one I use, which is called Voyager, it has a virtual dashboard and you can dial in your camera sensor size and your telescope magnification, and it will give you an exact kind of reference for what that telescope is going to see, and you can move it all around in pre-mapped areas of space through Aladdin and so forth, and then you can frame it, and then you can rotate it and do all kinds of clever things, so you don't have to necessarily just kind of plonk it right in the middle. Okay. Almost done. Colour palette is a good one to work with. This picture on the left is by a gentleman named Neil Creek. He's cleverly managed to photograph the Milky Way and all that blue and all that wonderful colour, and he's contrasted against over Lake Epilogue with the light pollution from Ballarat. And so you have these complementary colours of blue and yellow, which are opposite on the colour wheel, working beautifully together to create a harmonious image. Or in fact, on the image on the right-hand side, it's almost monochromatic with its colours. There's only 2 colours there, but they work beautifully to bounce off each other. So, as a tip there from the portrait photographer, if you've got blue eyes, wear something blue. If you have green eyes, wear something green. If you have brown eyes, wear something green or maroon or purple, because those colours are all working off the colour wheel. And if you do that, it'll look good in your photos. Okay. Same subject, different fields of view. So the one on the left is with a 1,100 millimetre focal length, and the one on the right is a 330 millimetre focal length telescope of what is strangely called the Running Chicken Nebula. Don't know what the guys at the Australian Anglo Observatory were smoking the day they named that, but there it is. If you can see a chicken, you're doing better than I am. But in that, with the close-up version, you can see this little coal miner down here stoking up the fires, and there's a little misty mountain there, and there's some Bock globules, which are star-forming regions. And sometimes zooming in on a well-seen object to get those details is perhaps even more engaging than seeing the whole thing. So, just food for thought. Stars or starless? That's a bit of a controversial topic sometimes with some folks, but I'll give you a little tip here that we've sounded out the judges of the Australian Photographic Prize, and broadly, probably shouldn't be telling you this, broadly they like images with stars. If they're astronomical images, because astro means star and stars have a certain shininess to them. That said, NASA liked the one on the right, and they published that as an APOD, because when you take those pesky stars away, you can see all the detail in the nebula. And you can see the Statue of Liberty's form there. Can you see that? Can you also see the Duran Duran keyboard player about to hit a note? Because the keyboard's right there. See? There's your keyboard, and there's the hand up, and he's, you know, about to do the thing. Pareidolia. It's cool. All right. Maybe leave the stars in. I don't know. And then finally, research. Next time you're going out to shoot something, think about what you're going to shoot, and are you just going to shoot the same thing that everyone else shoots, the same way that everyone else shoots it, on the same angle that everyone else shoots it, or maybe dig around, do a little research and shoot something that's never been seen before, like this image from one of the judges that I mentioned earlier, Marcel Dreschler. And this is really cool. This is a new discovery. Don't think anyone else has photographed it since, but they were the first. And something like that would certainly get the judge's attention. Last of all, a couple of wide field shots. And from Ari Rex, who does a lot of this wide field stuff, this is a pleasant composition, a nice image, and that's kind of the before version of it. And this is what he's done to tweak it to make it look even better. And you'll note here that if I go back, you'll see how this verticals on the little house there are now straightened. The detail is now popped in the Milky Way, and it's cleaned it up and made it a lot more dramatic, a lot more interesting. So there's a lot in the processing side of the photography that is always good to touch on. And I think the last one we have, you wouldn't think there's much in this, would you? You'd look at this and go, oh yeah, it's nice, yeah. Check this out. That's the same thing. That's the same actual file. Can you believe it? Look at that. I did a double take on that. It's like, what? You're crazy. It's pretty though. And it's well balanced, nice use of the rule of thirds. Looks pretty good. Amazing stuff. So there you go, guys. That's a little bit of show and tell and a little bit of an idea about some of the things that judges look for and they like to see in photos. And obviously those things apply to astrophotos in particular. Thank you very much. That's me done.
here we are with Astromofo. So our last Astromofo was the lunar eclipse and galaxies, and moving on to this one, which was supposed to be globular clusters, but thanks to the weather, there hasn't really been any photos taken lately, so we don't really have any globular clusters to show. I also wasn't at the last meeting, so we'll just go through the photos from the previous month's challenge, which was the lunar eclipse. There's quite a few of them that we got. There's quite a few members that got involved in it. And actually, who submitted photos for the lunar eclipse here? Anyone? Oh, there's quite a few. Heaps of them did. Heaps of people did. So this one here that we've got from Fred Prater, which was down at Pebble Beach, and he's put up a couple of photos on our Facebook page of the solar eclipse. I'll go through these a bit quickly because they were also on the Facebook. This one here from Charmaine Compton, and these are all the people that did take photos of the lunar eclipse and put them on our Facebook or socials. So Fred Prater, Charmaine Compton, Chris Black, David Rolfe, John Goodall, Nerida Langcake, Nick Axaris, Peter Skilton, Peter Skilton got a photo in. Peter Wiley, Russell Smith, Stephen Moore, Sue Stoner, and myself. So this one here with a Samsung S22. This one here from Chris Black, getting creative with a bit of smoke and mirrors, and some sunglasses to get this photo from a box. This one here was taken by myself using the MPAS solar telescope down here at the Briars on the day, and my Astro camera. And this one here by Dave Rolfe. Dave got this with his monochrome camera and the Lunt 60mm solar scope, so there's a lot more detail that you get in the monochrome cameras compared to the colour cameras, so some good work there. And a green ghoulish coloured sun by John Goodall. John's here somewhere. There he is. Nerida got this one with her Dob and smartphone. This one here by Nick Axaris, which is projection onto a pizza box, it looks like, from his telescope. And we've got a couple of solar anchovies on there as well. So well done, Nick. Peter Wiley with the Nexstar 6 SE over here on his one. Stephen Moore getting creative with putting solar sunglasses on his iPhone or his smartphone there and getting that photo. And here we've got Peter Skilton's efforts with his iPhone, and Sue Stoner getting creative with the binoculars there and giving us a interesting looking googly-eyed sun. So well done, everyone. The next one was galaxies, was the other part of the last challenge. And we've got this one here by Guido, who's here as well tonight. With about 320 minutes exposure of NGC 4945, which is spiral galaxy in Centaurus. And also in this photo, there's a couple of other ones. 4945A, which is another spiral, but that one's much further out. That's at about 62 million light years. NGC 4976, which is an elliptical galaxy. And that one in the corner over there, PGC 45001. So make sure you don't forget those numbers. That's around 80 million light years away. Guido, Russell Smith, myself, and Nick Axaris managed to get galaxy photos last month. These ones here by Russell Smith in HA LRGB, so it's got HA luminance and then red, green, blue filters on his 130mm refractor, and that one's M83. So M83 was also known as NGC 5236, and remember that because I didn't. And it's a southern pinwheel, which is in Hydra, just on the border of the Centaurus constellation, and it's really got some nice detail there. I've actually cropped that and zoomed in on it a little bit because I managed to get a bit of the nebulosity in that. And the other one was the Centaurus A, the Hamburger galaxy, which is actually a elliptical galaxy undergoing a merger with a spiral galaxy, apparently, and that's why we get that dust lane coming across that galaxy there. Then we've got a few efforts from myself, M83 in the top left, the Leo triplet in the top right, and NGC 4945 in the middle there. What else have we got? Nick Axaris sent these photos, again with Centaurus A in the top left, and also in on the right there he's got NGC 67. Oh no, yeah, NGC 6744, which is in the Pavo constellation. So well done everyone for getting the galaxy photos in. Now, because of all the clouds we've been getting, I thought I'd pick a more appropriate astro target for the next one. So clouds. Anyone wants to shoot some clouds? I thought if I pick clouds as the target, the clouds will go away. So now seriously, we'll continue with globular clusters. So if anyone wants to try and get some more photos of globular clusters there and submit them, that'll be good. Madeline McKenzie, that's Guido, Dave and me, by the way, photographing 47 Tucana. So yeah, globular clusters, we've actually got Madeline McKenzie from National University coming down for Vastrock. I think that's still happening, who is doing her PhD on something about globular clusters, and she's asked to see everyone's photos of globular clusters. So she'll be getting a copy of them all. So yep, get your photos in. Look, if anyone takes a photo of Omega Centauri, I'll put it in. I had said Omega Centauri wouldn't be included because apparently it's not a globular star cluster, it's a nuclear star cluster. And if you want to know the difference, Madeline gave us a good analogy, which I'll try not to scramble. But if you get, like, let's say you get an ostrich egg and you crack it into a bowl, you've got the yolk in the middle and the white of the ostrich egg around. And that's, let's say that's our Milky Way. And then you get, along comes a little chicken egg or a duck egg or something, and you crack that into the bowl as well. So you end up getting that all starts moving around. You get the egg white from the emu egg and the chicken egg all mixing in, but the little yolk from the chicken egg stays separate. And that is the nuclear star cluster that's left over. So Omega Centauri, no, yes, is thought to be a nuclear star cluster, not a globular star cluster. So there you go, one galactic egg analogy unscrambled. And sorry? Yes, if you want to know more, come to Vastrock. There you go, how do I do? All right, and who's the sidekick that we've got also coming? Brad Tucker, also coming to Vastrock. So get your tickets when they come on sale. All right, any questions, anyone? No? Very good, thanks very much.
I'm just going to go over some photos from an event that I attended recently down at Gippsland. So the ASV had been in discussions with Dave, who was the VP at the ASV at the time, and Destination Gippsland had contacted the ASV, and they're the main tourism organisation in Eastern Victoria region. So MPAS was approached by Dave to collaborate along with the Latrobe Valley Astronomical Society at some stargazing events down in Buchan to promote tourism using their dark skies as the draw card. So 2 members from each society were asked to attend. So Guido and I went down there. Guido's here tonight, but he's getting picked up by a taxi at 2 o'clock in the morning to go to Germany, so he's going to sit over there. So Guido didn't arrive till Saturday, but I went there on the Friday night before the big event on the Saturday. So this is the Stockman's Camp, which is where the event was held. There's a laser on this. So this drone image was taken by Chris Morley. He's the president of the Latrobe Valley Astronomical Society. So this is I'll give you a quick tour. This is the camping area. And we drive in down here, and then Guido had a little cottage that he shared with a member from the ASV. I had my own tiny house up the back of the property, so I had a beautiful view from there. This was the entertainment barn where the main event took place. And we set up our telescopes out here on the paddock, so there was a bit of a fenced off area just there. So all our accommodation was provided by Destination Gippsland, and This is my little tiny house, which was awesome. Being the only girl has its perks because I had to share with nobody. So I had really patchy phone reception down that end of the world, and that's no good for social media or me, but I managed to survive. Chris from the Trobe Valley, he shared with another gentleman from the ASV, and then Guido shared with, what's his name? Andrew from the ASV. So before we arrived on the Friday, I had emailed everybody from the different societies. We agreed to have dinner together on the first night because none of us had actually met each other before. So I booked a table for us here at the Buchan Caves Hotel, which is also owned by the same people who own the Stockman's Camp where we were staying the night. And I'd met Chris and Michael briefly from the other societies before we left, so they jumped into my car since I've got a people mover, and I drove us down to Buchan, and then Andrew from the ASV, he met us there at the hotel after going from table to table to ask everybody if they were from the Astronomical Society before he found us. But fortunately we had a common interest, so conversation was easy, and we all had our phones out showing photos like pretty quickly, so that was easy. When we got back to camp, we set up our telescopes just to work out who was going to be where, which way we were going to be facing, where our cars were going to park. And then after we had done that in the evening, we met with the owners from other businesses in the area who were also interested in perhaps hosting a stargazing event at some stage in the future. So we went over all the basics with them, like safety, expectations, planning, things like that. I hope no one's arachnophobic because this next picture's gross. So, if anyone knows me, I hate huntsmans. And I had a visitor in my room after we had our meeting with the other people. I went back to my room and there was this huntsman just being gigantic on my wall. It was disgusting. I walked in, I turned the light on, it was just there. I thought I could deal with it. I couldn't deal with it, it was disgusting. So I bolted out of the room, I ran over to my new friends of 3 hours, went over to their cabin and I went screaming up, help! And they thought I was having some sort of medical emergency. But I told them it was a huntsman, so they laughed at me and came over to try and remove it for me. And I made, Chris got it off the wall while Michael was standing there saying, gee, it's big, isn't it? Because that wasn't really helpful at all. And then I made Chris walk like 200 metres away to go and get rid of it because it was just gross. But then, after I had a terrible sleep with my light on, so I could see the walls for more huntsmans, the next morning when I woke up, I had this awesome view. This is actually, there's my bed. This is my view through the window. So that was nice. And then when I opened up my door, I had cows and it was so noisy. It's quieter where I live in Narrabri South. It was so noisy out here. Kookaburras, cows, cockatoos, pigs, roosters. Guido had a chook pen outside your room, didn't you? Yeah, I didn't have that. I just had all this other stuff. Oh, the huntsman, that was the worst. Give me all the other things over that huntsman. That was disgusting. So we agreed to meet the next morning for breakfast at the local cafe since we had nothing on for the rest of that day. The cafe across the road from the pub, it's called the Willow. That was awesome there. We had a really delicious breakfast. We sat outside. All the locals seemed to like visitors, so they all talked to us as they walked past. And we went back there the next morning as well because it was so nice. After that, I went for a bit of a drive because Guido wasn't arriving till later that afternoon. So I thought I'll go and do some sightseeing, and I found a pretty disappointing waterfall because there'd been no rain. I found a cute bridge. I went back to the camp and had a look around there. So there were some resident pigs. We had some ducks. They were all very noisy in the morning too, but I went, yeah, look through that before Guido arrived. And then over here, this is that bit down there, that's where the campers were setting up later on that night. All these fire pits got moved because that didn't mix well with telescopes, and in the dark you would obviously trip over them. And then the live music was set up in the stage that's there. So the campers started coming in the afternoon, that's them setting up down there. And then some of them set up in other areas of the camp as well. I don't know why they would go there because they're actually a long way away from the amenities, but I guess it had a good view or something, I'm not sure. We were setting up our telescopes in this fenced off area. There's a white rope to fence it off. So we had all our telescopes set up nice and early. This is Guido just here, setting up his telescope. So this was Guido's telescope that he had. He had his 10-inch Newtonian on an AZ EQ6 mount, and then he also had his 73mm refractor on an AM5 equatorial mount. There's another view of us setting up our telescope. So we had lots of room to spread out. We moved our cars along the fence line so no one tried to drive through that way. Some members from the other societies. So this is Frank from the Latrobe Valley Astronomical Society. He actually was previously a member at MPAS a long time ago before he moved from the area, and this telescope here, Greg helped to build, I believe. Yeah. So he still uses it. That's his daily or nightly. So after we've got Andrew setting up his 5-inch SCT, so he's from the ASV. Frank seemed to be in every photo. I think he was doing a telescope tour. So this is Michael from the ASV with his 12-inch collapsible Dob and Frank again, and then there's Frank with Guido, checking out his gear again. And there's Guido and myself with his 10-inch reflector and me with my Dob. So we had lots of different telescopes there for the evening. So they provided a 2-course meal for us as well. That was part of the, when people bought a ticket, they got a 2-course meal and stargazing. So we had, this whole area here was all tables. There was tables outside over there. They had like a whole servery set up inside, and then they had their live music being played over here on the stage as well. And then all these lights in here, they all got turned off when it was time to do some stargazing. But the clouds didn't cooperate that night. So throughout the day, we'd been checking cloud-free night, and we all knew that the clouds were actually coming. So we had this really nice sunset before the clouds arrived. And Chris took this great picture of the crescent moon before it set and the clouds started rolling in. So we finished our course of roast dinner, and we decided to go out to look at the sky right then because we could see the clouds were about to come. So we went outside. Chris did a really quick sky tour for all the guests. That's a safety talk, and he used his laser to show them where things might be. And then they roamed around the telescopes for, how long, Guido? 20 minutes before we were totally clouded over, totally. So obviously it meant it was time for dessert. So after our apple crumble and ice cream, Chris gave an awesome interactive presentation that had props, and he asked the audience lots of questions and they asked him lots of questions. One of the things I liked about his presentation was he had a ball about this big. He said, imagine this is the Earth. He had another ball about this big and said, this is the moon. And he got kids to come up and take the moon ball and say, walk how far away you think that moon would be from the Earth if it was to scale. And none of us got it right. Like none of us from the societies got the answer right. It was embarrassing. The kids, does anyone know how far away they would walk? If the Earth was this big, if the moon was this big, Jamie's trying to work it out, 7 metres. He moved away. We were like way off, weren't we, Guido? So we had great feedback from all the guests on the night, and the camp was really well organised with all their dinner courses and their accommodation. It was all laid out. It was really, really well done. So the next collaborative event between the same societies at Locksport this weekend, Friday night, I believe, is already sold out, and there might be tickets left for Saturday night. Dave, do you know? It's maybe sold out. Yep. And I really like transitions on PowerPoint, by the way. I just thought I'd throw that in there because I like the curtains. So, thank you. Next month's meeting, we'll have a revisit to the South Pacific Star Party that a few of us went to a couple of weeks ago as well. So we'll do that next month.
Well, before I put this one on, I'll say we'll break for a bit of a tea break now for 15 minutes. So going on the clock over there, that's until about 25 past 9. Then I'll start the talk in here on physics and psychology of colour, given by someone who's worked for the National Physical Laboratory in the UK. That's the equivalent of NATA here in Australia, the National Association of Testing Authorities. And he's spent his career measuring colour, so he knows the subject very, very well. And then we'll look at how rainbows form, the different types, and then we'll close with Kilauea erupting again. All right, so if we come back in at 9:25 on the clock up there, feel free, and if you wish to stay out there and socialise instead of coming in for the videos, that's perfectly fine as well.
Please welcome onto the stage Andrew Hanson. At the end of this talk, you may be convinced that the four colours shown here are identical. Colour is that crazy. So let's press on. Does anyone remember the dress? Big social media thing about 3 years ago. Somebody shared an image of their wedding dress and the world went wild, arguing about its colours. We'll go into that. I bought the dress. My daughter was too young to fit into it, but there she is standing next to it. And I took a photograph. I illuminated it brightly from one side and dimly from the other. And in one photograph alone, we can pull the bits out and we can see that indeed, under some conditions, it looked white and gold, and under conditions it looked blue and black. A conference was held to discuss all the various implications of this. The Colour Group of Great Britain, all of their committee were approached by a number of media outlets. I was approached by the Telegraph. I had a column written in there. My mother was delighted. My father was disgusted. He said, "You should have been in the Guardian." Before I move on, I'd like to tell you who I work for. The National Physical Laboratory, or NPL as it's known in short, is the National Measurement Institute for the United Kingdom. We have about 1,000 people all measuring stuff on your behalf. When it was set up about 100 years ago by the Royal Society, it was actually, well, they call it the National Physical Laboratory. I think they should have called it the National Measurement Laboratory. We do physical measurement there. And for 20 years of my life, I was engaged measuring colour and light. And that's the basis of what I'm going to talk to you about today. But the building itself, well, it keeps everything running for us. You may not realise it, but we rely on measurement. Every aspect of 21st century living, and before, relies on knowing how much you've got of things. Nuts need to fit bolts. You need to know that the ingredients, the active ingredients in drugs are the right amount, and so they're measured really accurately. And most importantly, when you buy chocolate, you need to know you've got the right amount. So weights and measures and all sorts of other measurements are really, really important to make the world work. And that's what we're there for, doing it for the UK. Set up about 100 years ago in the corner of Bushy Park. And we moved about 10 years ago into a nice, big, new, glamorous, white building with 388 separate laboratory spaces, some of them very large indeed, with very odd things going on. All measurement, though. And since the 1910s, we've been involved in measuring colour and light. Electricity has only been brought into our houses for about the last 100 years, and it was brought in not to run television or iPads or heaters, but light. So measuring the efficacy of lighting systems has been in there for pretty much 100 years now. We use colour every day, and there's a photograph of the outside of this building. And in just one scene, we can see the use of colour in branding. And it's really important that those brands, once they've been sorted out, are shared appropriately with the right colours, that your web page has the right colours, that mugs and clothing and printed materials all look the same colour. So branding is really important, and we need to communicate the colour of these brands appropriately. Quality control. Imagine if your car got dented and needed a respray. You need to be confident that the colour of the respray fits with the original colour of your vehicle. And finally, legal and safety. There are lots of yellow lines and white lines out down this road just outside. And there are rules about how visible those lights, those lines need to be. So people go out there and measure them all the time. You need that for visibility. We also use colour to manipulate emotion. So there's a lovely view graphic up there of all sorts of colours for brands. Maybe you recognise some of them. And according to the people who created this, this diagram, you can associate particular emotional responses with different colours. Gets you thinking, doesn't it? So there's a need to measure and specify colour. Let's quickly pick apart those needs. You create a brand or an identification system, which really needs colours to be communicated correctly beyond language to other parts of the world who might be creating things on your behalf. You also use it in monitoring processes such as creating paints, but also I bet if you go into a shop and you're faced with a huge amount of orange juice, if one of those containers contains something that looked slightly different in colour to the others, that's the one you wouldn't buy. So in monitoring processes, colour's used quite a lot. Now, if you're communicating colour, you need to talk about absolute values. You need to be able to recreate exactly a colour remotely, and that requires an absolute definition. But if you're monitoring changes in things, maybe you're just interested in difference values or things relative to the target colour. Now, these have their different requirements, but they'll still require some precision in colour measurement. Now, we are humans, and we have a visual response to light. Light has wave properties, and we can split light up according to the wave properties. So I've brought along a little demo here, which I hope will work. Can we dim the lights a bit, James? I've got a very nice fancy light bulb here, and I'm going to dazzle the guys over there. There we go. Can you see that? Good stuff. So we have a mixture of white light coming on here, and this thing here acts a bit like a CD. Have you ever held a CD up to the light and seen all the bright colours coming out of it? It does the same sort of thing in a raindrop as well. And it splits the light up into its various components. So from this direction, we have the blue of a light-emitting diode shining through a phosphor that generates other parts of the spectrum through the process of fluorescence. And then up here, we've got the whole thing starting again, because that's the way this system works, unfortunately. So we've got the next lot of blue overlapping. But if we could just look at one spectrum remotely, just one spectrum, then you'd see it going from violet, blue, indigo, well, the colours of the rainbow. Let's see what I've put up next. So, and our response to that spectrum varies. We don't see all colours evenly with the same amount of response. At the red end of the spectrum, the amount of energy in red light is not enough to excite the photochemistry of our eyes, in our retina. So we become blind to anything beyond a particular wavelength. We can't see infrared. Some animals can. At the other end, we can't see ultraviolet. Ultraviolet radiation has the potential to destroy the subtle chemistry and biology of our eyes, so we don't want it to come into our eyes. And the filter at the front of our eye is the ciliary lens. Something normally used for organizing light and focusing it also acts as a filter, so we cannot see ultraviolet radiation. Some animals can. And somewhere in between, at the peak of the green part of the spectrum, that's where our eyes are most sensitive to light. So as a physicist, I would say you need less watts of green light energy to excite a sensation of brightness in the eye than you need for the red and for the blue. You need lots more energy to excite the eye if it's red and blue. Let's look at two objects. I'm going to do the whole lights down again. I brought two objects along here. Can you kill the lights again? Thank you. Right, I'll see if I can get a slightly brighter spectrum. It's looking a bit dim to me. There we go. Try. Oh, that's a bit better, isn't it? Let's choose that one. Okay. Got two objects in my hand here. They're actually bits of gaffer tape. And if I go from the blue end of the spectrum, can you see they're both quite dark? But as I go for a little walk, out here, cyan, green part, this top part that's a piece of green tape, looks really, really bright. As I move into the yellow, at some point, the two will appear equal lightness. Is that happening for you? And then as I go out into the red, the green part becomes dark and the red becomes violently light. Now, it's really interesting that people's responses to light are different. The cameras seeing this as well might see these slightly differently. So you'd all argue about which point the two look equally bright. That's quite normal. We are all individuals. Now, as a measurement scientist, well, that's great, but where are the numbers? And more importantly, where's my controller? Here it is. So we can measure things. And I said that light has a wave property. We talk about the wavelength of light. So I've written those along the bottom there. The numbers are actually 1,000 millionths of a meter, or nanometers as we call them. And we can only see quite a narrow band of wavelengths, from 380 in the violet to about 780 nanometers in the red. So we popped these two objects and we measured their spectral reflectance, how much light they were reflecting as a function of wavelength. And there they are. Can you see? Two lines. Now, the green line shows us that the green object was reflecting a lot of light at the green part of the spectrum, but not much at the other extremes. The other line, which I've made cyan so that you can all see them nice and clearly, is only reflecting light at the red end of the spectrum. Now, that property is something to do with this material. It's nothing to do with the light bulb, it's nothing to do with the way we see it. That's a property of the material. Let's have a look at the 3 stages of colour production. You can have many, many different types of light source, all with different spectra. And they will shine onto different things that diffuse and scatter and reflect and absorb and transmit light differently as well. Again, with a spectral property. And then we resolve those spectra with our eyes. And if we need to, we train artificial intelligences or robots or cameras to see colour the way that we do. So colour is a 3-stage process. Something to do with the light source, something to do with something that changes the colour of the light source by absorbing or whatever light, and then the way we see it as well, a 3-stage process. Now there's quite an odd thing that can happen. This observer is looking at 2 things and they appear the same, okay? They appear the same. And this observer sees them and they appear different. And the reason is that the eyes sense things differently. Okay, can you see that? And we call that observer metamerism. Now let's move to a different situation where you have one eye looking at 2 things and we change the colour of the light source. Then we have a sample metamerism issue. And you might remember when cloth, you went into Marks and Spencer's or whatever and you compared 2 things and they would look identical in colour under one type of lighting but different in colour under a different type of lighting. I can see a lot of people nodding their heads. They'll only match under all the different types of light source if they actually reflect light identically. And it's quite unusual to get things to do that. So here's your typical O-level question, GCSE these days. If you have a blue object illuminated with a blue light, what colour will it appear? Anybody venture an answer? Somebody said white, somebody said black, somebody said blue. I've seen the marking scheme. It says if you shine blue light onto a blue object, it will appear blue. That's supposed to be the easy question. Here's the harder one. If I have a red object and I illuminate it with blue light, what colour will it appear? A unanimous black, fantastic. I guess you understand that red should absorb, or red objects should absorb the blue light, leaving nothing to reflect. And that indeed is what the marking scheme will give you 2 points for. but it's wrong. On 2 counts. What if the thing was shiny? It would reflect some of the light. There you go. And we call that specular reflectance. So you could argue that I'm just seeing the light itself, but you know, the thing is reflecting that light. So you could have a red object that kind of looks bluish because you're seeing the reflected light in it. A mirror reflection. What about this? It could actually look red because we have a thing called fluorescence. I'm sorry, I'm going to go back to this demo yet again because it's such a good demo, this one. Can we get the lights down again? This is the last time that we'll mess around with this. I've got here a yellowy object. It's a high visibility jacket. So I've got yellow light coming onto a yellow object and it looks yellow, okay? What if it was blue light falling onto a blue object? A yellow object. Oh my goodness, it still looks yellow. In fact, it doesn't really matter what I put this under, it will be a yellow of some type. It really doesn't matter. And down here, we have high energy, blue light, losing some of its energy in the chemicals inside here, and re-radiating at lazier, lower energy, yellow part of the spectrum. We call that fluorescence. Makes measuring an absolute pain, because you put one type of light on and you get another type of light off, which seems just stupid. And not in the marking scheme. What makes colour? Well, there's a great book called The Physics and Chemistry of Colour, The 15 Causes of Colour. It's by Kurt Nasu. Pretty much each chapter deals with a different reason for creating colour, and as a physicist I was quite upset by this book because it all seemed to be chemistry. A lot of it is to do with electrons and how they move, how they absorb, and how they radiate energy. But that's only half the book, there's the other half. And there's some physics creeping into the later chapters. Let's look at some of it in practice. In autumn, leaves go through a series of incredible colour changes, all to do with the chemicals inside. Now, normally you'll have chlorophyll in a leaf, very complicated molecule that wiggles at some frequencies and absorbs energy. It's using blue light, violet light, and red light, collecting energy at these wavelengths, but it's reflecting the green light. It's not using the green light at all. So we just see what the leaf doesn't need. As the leaf dies, we then see the carotenoids. Now, chlorophyll is actually quite a weak molecule. It'll fall apart quite readily. So they have carotenoids in there to mop up free radicals that would otherwise destroy the chlorophyll. So those chemicals are in there to keep the thing going. They're also the reasons why carrots are carrot-coloured. I guess there's a connection with the name. And finally, as the leaf dies and the chlorophyll stops working and the carotenoids stop working, we're left with anthocyanins. Anthocyanins are a set of dyes that change their colour with pH, from violet to pink. And it's no coincidence that the names violet and pink are colour names, but also flower names. So how do we see colour? I'm going to do a human experiment on you now. Can we dim the lights a little bit, James? Can you see the doodah in the middle of the elephant? Yeah, stare at the centre of that. Don't look left, right, up or down. Just keep staring at that. Okay, and in a moment I'm going to remove the image, you're going to blink a couple of times, and then you're going to make an R noise. Are you ready? Blink a couple of times. I can hear the R noise. That's good, that's perfectly normal. Different parts of your retina were getting bored at seeing those colours, and so they switched off. They literally became blind to those colours. And so when you see nothing, you see the opposite of that colour. Should we do it again? I've got a different image. Stare again at the centre. Keep staring. Don't look left, right, or up or down. We don't want that image to be blurred. I want to burn this image into your retina in a non-blurred fashion. I guess you recognise the shape. Don't look at the shape, just stare at the thing. And I guess you can see where this is going. Okay, blink a couple of times. It's wherever you look. It's on the ceiling. It's on your neighbour's face. It should go after a day or two. Can you tell me what the blue turned into? Yep. Can you tell me what the yellow turned into? Blue? Yep. Can you tell me what the black turned into? Yeah. Every colour has its opponent colour, an opposite colour, the evil other half. And designers know about this colour, and they go, you can't get any different between this colour and its complementary, its opposite colour. The scientist Maxwell used these after-image colours to analyse how people saw colours, and people with different vision defects, colour blindness, see different after-images, and from that you can work out how we see colour. I did this talk in Belgium. I felt I should use the Belgium flag. It didn't work so well for me. The audience were all going, ah, but I just didn't. It took a long time for me to see the colours. And that got me thinking, it's not just what you're seeing, it's what you think you're seeing. It reinforces what you see. And a little bit later, after doing that talk, I was walking down the road and I saw someone with a leather jacket on, with the Union flag on the back. It was late-ish at night, and from a distance with the ill illumination, I wasn't quite sure what I was seeing, but I could pretty much see the colours. But when I got really, really close, I found out that there were no colours on there at all. It was just in black and white, and I was imagining those colours. You can see things that are not there. Do you remember that first slide? We're working slowly towards that. Colour's quite complicated. If we look at the response of the human eye, there it is, and it looks like someone's thrown a psychedelic bedsheet over some furniture. And they have. There are some details missing. Let's remove that and look at the details. We have 3 types of sensor in the eye, responsive to different parts of the spectrum by different amounts. There's one line there that shows that something is responsive more to the blue end of the spectrum than the others. There's another one that's more to the red end than the others, and there's something more responsive to the middle part of the spectrum. And these 3 different signals from this mosaic of sensors in the retina gives us the sensations of colour. Colour is a 3-dimensional perception. And this is a machine that you can use to investigate how we perceive colour. This was built by my boss, Julie, in the 1980s, and there she is doing some experiments. She was repeating experiments that were done in the 1920s by WDW, as he was affectionately known, and John Guild. And this is what they did. To see light, to see colour, you need light in the first place, and that accommodation level will affect how you perceive light. So we set a sort of general field at daylight viewing conditions. We took a spectrum, and we grabbed just part of that spectrum. In this experiment, we're taking the cyan part of the spectrum. And then we ask observers to tell us how much of 3 primary colours, selected from different parts of the spectrum, are needed to match that colour. Can you imagine in your mind how much you'd need of blue, green, and an orangey red to make cyan? Let's have a go at doing that. If we had equal amounts of the first 2 primaries and no red, we'd actually get a very poor match. So observers in the 1920s and in the 80s were allowed to twiddle the knobs and adjust it to create a decent match for them. And it doesn't always work first time, but eventually you'll get a reasonable match. Now, can I tell you that the actual settings on those dials will vary by person, by illumination level, by eye. But you can end up getting an appreciation of how individuals see or sense colour. And in the 1920s, those data were combined to create what we now call the standard observer. That's the data all pooled together. And we created a colour chart based on the human perception of colour. There it is. And in 1931, an international committee agreed that this is the chart that we will use from now on. And today, that human model, based on those 17 observers, is embedded in cameras and projectors and television and iPads and any colour rendering system. Even traffic lights. Oh, I did say that colour is a 3-dimensional thing, but this is a 2-dimensional plot. We're losing something, aren't we? There aren't 3 numbers being represented here. What we are not representing is the lightness of the thing. So this is sort of a slice through a piece of psychedelic ham. with lightness coming out of the paper. You can imagine the third number telling you something about how bright it is. Anyway, traffic lights. There's a British standard about what the colour of traffic lights should be. There they are. The reds should be in that little red area down the bottom, the greens there, and the ambers there. Why? Because we don't want people to confuse the different colours. Now, you can actually plot colour blindness, colour confusion lines for people with colour defective vision on this chart. Let's pop them up there right now. There they are. And can you see how everything along that, each one of those black lines, that would be confused as being a similar hue for someone suffering from deuteranopia, a type of colour blindness. Can you see that there's no line connecting the red with the green? Can you see that? So that's great. Those people suffering from that kind of colour defective vision won't confuse the two types of traffic light. But there are three types of colour blindness because there are three types of sensor in the eye, and there are three things to go wrong, and those are the other charts as well. How do we measure colour? Well, we could take a photograph of the spectrum. Here we have some white light coming in and shining onto one of these gratings, like I just showed you here, and you can take a photograph of what comes off. And you can compare the photograph of the spectrum with a photograph of a standard spectrum of a standard lamp that you know how much light is coming out at each wavelength. And from that, you can infer exactly how much light is present and then pop it through a model of the human eye, and then you can plot it on that colour chart. Alternatively, you could do the cheap and easier version, which is just measure the amount of green light, the amount of red light, and the amount of blue light, the same way that the eye does, get out three numbers, and again, that would give you a reasonable approximation. This is the way that cameras work, of the colour that you can see. And so we can use that to measure creme brulee, or whatever you like. But perceived colour is oh so much more than just amounts of red, green, and blue. This is the second part of my talk, and this is why I basically stopped measuring colour, because it just becomes so complicated. It moves from physics to biology and psychology. And so let's do another experiment on you. By the power of PowerPoint, I'm going to rotate a piece of white so that it obscures these little dots one at a time. It's going to do that, okay? Can you see? So let's do it. And while it's doing that, I'd like you to stare at the cross in the centre, and something weird will happen. Keep staring. Keep staring. It'll vary. The experience will different. People will be different. But what a lot of people see is that initially you see a kind of green thing going around, and then maybe you only see the green thing going around. Too weird. I'm not going to explain that one. It's too complicated. I'm going to tell you where all these changes occur from, though. So we have a mosaic of red, green, and blue sensitive cells at the back of the retina. And exactly how they're distributed and the proportions of them will vary, and that's controlled by your genetics. Someone took a photograph of the different types of cell in the back of the eye and coloured them in with a felt tip pen. That they really aren't this colour. This is just to show you the different responsivities of different parts of the eye and different people's eyes. And so this really does mean that different people can sense colour differently. I built a machine to measure how shiny cats are, because someone wanted me to. And when I did that, I realized that we don't see light linearly. Different equal steps of increase in light don't appear to us as equal increases in light as perceived. We have a very non-linear response to light. So there I've got the whitest thing that the projection system will display, and the darkest thing that it will display, labelled 100 and 0. Where do you think 50 will be? Let's put it in. Does that appear to be exactly halfway between the other two? No. Again, we can do experiments and you can start messing around with it, but we have a non-linear response to light because we have to accommodate such an enormous range of light levels. Age. There's my dad and my daughter, many years between. Now, my dad's eyes have been radiated by ultraviolet radiation for a very, very long time. So they've yellowed with age, which basically means he's not getting so much blue light going to his retina. So for him, if I divide the picture on the left-hand side, he'll see everything literally through sepia tones, whereas my daughter will see blue things a lot brighter. Light level. We have another type of sensor in the eye responsive to low light levels, which actually gets more excited by the blue end of the spectrum. So if you go into the bluebell wood late at dusk or at dawn, there's a reason to do it, you'll see that bluebells look suddenly a lot brighter, and yet they look less colourful. So the way we see colour varies with light level a lot. Have you ever done decorating? Did the colour come out the way you wanted it to? There's two things going on at least. One is that as the light comes in, it gets mixed around, and so it will affect the other colours in the room. The other thing is that when you're looking at a colour swatch, you're seeing an area that's different to the whole room being painted that colour. The majority of the colour sensors in the eye are located in the centre 2-degree field of vision. That's a thumb at arm's length. That's where you're most sensitive to colour. Beyond that, there's not so much sensitivity. So depending on the area of the thing you're looking at, you will literally respond to the colour very differently. So I did a kind of mind experiment. What do we actually see? What's actually going into the brain? Well, the first thing is that the eye's a pinhole camera, so the thing's upside down. Secondly, if we mark in 10-degree slots, there's a blind spot. I've marked that in black in this image, where most of the light, well, it's not being received at all because you just don't see it. The cabling carrying the signals to the brain obscure it. And then also, can you see there's a little white disc somewhere in that picture? That's that 2-degree field of view. That's the bit that is most colour sensitive. So really, that's what's going into the brain. What an amazing fix-up job that brain is doing for us. It remembers what's going on. For fun, we used to exploit this chromatic adaptation property. At MPL, where I work, we had a big machine for measuring light bulbs, a big sphere that you could walk inside. And for fun, we used to put a green light bulb in there. People would go in, they'd be amazed at the fact there were no ceiling, floor, or wall, and the acoustics were great. And while they were in there enjoying it all, their eyes were getting bored with the colour green, so when they came out, everything looked pink. Colour constancy is an odd one. When you look at a scene, you refer everything to the whitest thing in the image. So here, I guess it's some of the lettering. And things look greener or yellower or bluer than that. And the eye is very good at adjusting. So again, the banana in this scene looks the yellowest thing and the orange looks orange. But in an absolute sense, in this image, the grape and the orange are actually identical in colour. And the two colour blocks down the bottom are actually identical in colour. So the eye does some pretty odd things, or the brain does some pretty odd things. And in fact, we have things called special colour cues. So bananas always look yellow, independent of what colour they actually are. Some great titles of scientific papers. If it's a banana, it must be yellow. The role of memory colours in colour constancy. Nearly finished. I've got a few more little curious demos to show you. This is such a good one. It got nicked. I had to take a photograph of it. Do those two bits of pink look the same to you? They kind of do, kind of don't. The more you stare at it, maybe they do, which is interesting. It's all dynamic. It varies with time. Because of what they're next to, colours affect each other. And in fact, those pinks are identical, but... and then if you stare at it for long enough, they appear to be the same, and then if you look away and look back again, the image comes back. The effect comes back. And it varies with field size. So if I do that, they really do look very different indeed now, don't they? Artists know about this and they exploit it. So Van Gogh used to have green next to orange because they made the orange look more orange and the green look more green. And yellow stars in blue skies, so that the yellow looked yellower and the blue looked bluer. This is a really weird one. The areas labelled A and B, do they look the same? No, they are. If I put that there, I've got a block there, and the area labelled A right next to it looks the same, and B looks right next to it, and the thing is uniform in itself. So they really are identical in colour. Would you ever, would you, it's crazy, isn't it? Three things going on here. B is in shadow. Things in shadow look lighter than they really are. We open up the lightness of things in shadows. B is surrounded by dark things, so it looks lighter than it really is. And the third one, this is the weirdest, this is the one I worry about most. You recognize the pattern. You know that B is light and A is dark, and what you know is actually influencing what you're seeing. Is that mind control? Is that scary? If you wanted to get machines to see color and light the way that we do, you'd have to program all of this into them. You'd have to measure the contributions and the effects. You'd have to get the machines to recognize the patterns and measure things that are around the things that you're looking at. This is my last slide. It's quite a complicated slide. I'm going to move that there. Can you see that the green next to the green is green? But if I shrink it down, we have a... Does it still look green? Depends where you're sitting, depends how old you are, depends on so many things. What about this one? It is the same green. The only thing I'm doing is changing its size. But does it still look green? Does it look the same green? No. So depending on where you're sitting, I mean, that might look a bit like that. That might look a bit like that. Again, we can tweak this for personal taste. It gets worse. Look at the eyes. Do the eyes look the same? If I do this, maybe I'll say those two are the same, yeah. Maybe the eyes are a little bit darker, but does it look cyanish in hue? Or does it look grey? You can see where this is going. Those two eyes are identical. So, we see these identical. This is where I began, this is where I'm going to end. Thank you.
Surely you've seen a rainbow. Maybe you were chasing tornadoes and happened upon one. But did you ever notice that the sky is darker above a rainbow than below? I never did until someone pointed it out. We're gonna find out why this is so with the help of refraction of light, dispersion, and the incomplete story you're usually told about why rainbows form. This story starts with refraction, the bending of light as it moves from one medium, like air, to another medium, like water, at an angle. Light actually slows down in water. Visible light would take 11 minutes instead of the usual 8 to get from the sun to the earth if there were a giant ocean in between. So as light slows down when it enters water, the beam is forced to turn. But unlike the constant speed of light in a vacuum, the speed of light in water depends on the color. Violet light moves slower in water than red light, so it will bend more as it enters the water. An incoming beam of white light will be spread out and separated into a spectrum of color. We call this dispersion. Now let's take this white light beam and send it through a droplet of water. Some of the light will refract into the droplet, then reflect off the back and refract back out to travel down to your eye, typically at an angle of 42 degrees between the incoming light and the outgoing light. This can occur in a circle of droplets, so if the ground weren't in the way, rainbows would be a full circle. Here's the fun part. Violet light refracts more in the water droplet than red light, as we discussed, so violet light should end up exiting higher in the water droplet than red. But if we look in the sky, red light is clearly higher than violet light. What's going on? Well, if you're observing from down here, this water droplet will only send red light to your eyes, and the violet light will pass above you. It's the droplets down here that send violet light to you, and the violet light will appear to be coming from lower in the sky, as it does. And that's how we get our colors in the rainbow from rain and sun. End of story. But there's one part I never understood. Why should all of the light enter the water droplet right at this point? Well, the answer is it doesn't. Some red rays enter here, some enter here, and they all exit in different directions. If we add back in the other colors, you end up with an exiting jumbled mess of color. This mess of color should look white, but it definitely doesn't. So what's going on? This is where it gets more complicated than you usually hear. As this red light ray enters higher from the midpoint, it exits at an increasingly large angle. But watch what happens here. Eventually the ray turns around. No matter where red light enters the droplet, it can't go past this angle. That's the maximum angle, and it's 42 degrees for red light. It's slightly less for orange and yellow and so on until you reach violet, where the max angle is 40 degrees. So it turns out that at that maximum angle, you also get a maximum brightness. So even though all the colors can reach here around violet's max angle, because their maximum is beyond that, violet is at its maximum brightness, so it stands out against the other colors. Same goes for the max of the other colors. Below violet, no colors are at a maximum, so all the colors mix again and form white. That's why the sky appears lighter below the rainbow than above. None of the light can make it out above red, so the sky appears darker. Then how did this second rainbow sneak up there? Well, you'll notice the colors are flipped in order, and again that the sky is lighter above them. That indicates that the light had to reflect twice inside the droplet. In order to get the right angle down to your eye, it actually had to enter the droplet from below the midpoint, and you get a double reflection, causing a second rainbow. Now the story is complete. The end. So a little while back, I was walking around the bay in San Diego when the view struck me. I saw this picture of something that looked like, kind of like a white rainbow. I thought at first it was maybe a cloud, but that's a weird placement and shape for a cloud coming off the bay. It looked like part of a rainbow. Not a great view. But I took a picture of it. This is the best I could capture, and then I forgot about it until months later. I saw some articles on the internet pop up about white rainbows. These ones are much more defined than mine, but clearly a thing. These are beautiful. I wanted to know what these white rainbows are, and it started me thinking about all the different strange rainbow phenomena that I've seen out there, like the rainbow circle around a plane shadow, the little rainbow gems in the sky a few angular degrees away from the sun, circular halo rainbows, and perhaps the weirdest of all, this one wasn't mine, but someone sent this to me, rainbows on a lawn covered in spider webs. Let's find out why all these different kinds of rainbows form and why they're so much more unusual than regular rainbows. First of all, how does a regular rainbow form? Well, it starts with refraction. We can't do rainbows without refraction. Okay, there's this weird thing that light does when it goes from air to water. It bends. This is called refraction. Yay, love that word. And it happens when light goes from air to glass, glass to water, anytime light passes the boundary between one medium and another at an angle, as long as they have a different index of refraction, which is a number that describes how fast light moves through the material, because light doesn't go at light speed through materials. It only goes at light speed through a vacuum. Light goes slower than the speed of light through materials. Maybe you knew. Now you do. So the index of refraction describes how fast light goes in the material, and it also describes how much light is going to bend when it goes from a material with one index to a material with another index of refraction. Got it? Cool. But the index of refraction, which you now are very familiar with, often depends on the color of light going through the material, which is something they don't usually tell you in physics class. So, for example, violet light bends more as it enters water than red light would bend. So what happens is an incoming beam of white light, which is composed of all the visible colors of light, will get spread out and separated into a rainbow spectrum. And this is just because violet and red light travel at different speeds through materials. That's kind of interesting. That's whatever. Okay, now picture a beam of sunlight entering a water droplet, which we're gonna pretend are spherical, even though we all know they're shaped like this, thanks to people who study water droplets in wind tunnels. So, beam of light hits the droplet, some of the light will refract into the droplet, then reflect off the back, and refract, it's gonna bend again when it goes from water to air, so it's gonna refract back out to travel down to your eye, typically making an angle of 42 degrees between the incoming and outgoing light, also known as the socially confident light. Is that a bad joke? Do you get it? And that's how rainbows form. Droplets of water in the air are spreading out beams of light so that some droplets are sending red light to you and some droplets are sending blue light and violet light and yellow light from different places in the sky, because the different colors are coming out at different angles. And you can get that 42-degree sweet spot with a circle of droplets. So if the ground weren't in the way, then rainbows would be a full circle, which is what some people get to see when they're in airplanes or higher above the ground. Which is not to be confused with these interesting rainbow photos, which are like halos around the sun. These are often called 22-degree halos, which is nice and descriptive, because if you take the whole view around you as 360 degrees, then the halo would be about 22 degrees of that. And they're caused by millions and millions of tiny ice crystals in the atmosphere. The ice crystals have a different shape and structure than water droplets, so you're gonna get the light reflecting and refracting out at different angles than if they were going through water droplets. That's why it's at 22 degrees. I actually took this picture. I love rainbows. And this one was taken by my mom back home in Hawaii, which is a double halo rainbow. I'm not gonna get into how double rainbows form, which is interesting, but it was so YouTube 10 years ago. But these halos are not to be confused with these rainbows often seen around airplane shadows. Yeah, I took these ones. These are called glories or pilot glories because they're typically seen from airplanes looking down at clouds, but sometimes from high mountains looking down at mist or clouds. And they're caused by light interacting with tiny water droplets. Like, we're talking droplets that are only the size of a few wavelengths of the light. The water droplets that are in clouds and in mist that are just kind of hanging out can be up to 1,000 times smaller than raindrops falling from the sky. So raindrops are typically on the order of 1 millimeter, and mist droplets can be as small as 0.001 millimeters. What is that? 1 micrometer? Yeah, micrometers, tiny droplets. So the droplets in clouds making these halos are a lot smaller than water droplets and therefore interacting with the light in a very different way. In fact, they're interacting with the light in a super complicated way. One source I found describing how the halos formed cited geometric optics, the complex angular method, and catastrophe theory as part of the explanation for the glory, so we're not gonna get into that. But I've linked to the source in the description if you're morbidly curious. Stepping back a bit to those 22-degree halos, there's a related phenomenon called sundogs that I usually see as what looks like a little gem of rainbow in the sky. But if you get a really good one, you'll see the 22-degree halo with bright rainbow spots on either side, and these are caused by light passing through hexagonal crystals in the atmosphere. We all know from snowflakes that water forms these amazing hexagonal shapes when it's in its frozen form. And so tiny hexagonal ice crystals can form in the atmosphere and orient themselves so the crystal face is almost completely flat as they fall slowly through the atmosphere. So you get more concentration of the 22-degree light refracting on the horizontal edges. So this all relies on the weird shape and properties of ice crystals, the fact that we have gravity to pull them and make them flat, the fact that we have an atmosphere to orient them, and the place of the sun in the sky. So these often form when the sun is low, close to the horizon. Cool. And if you get a really good sundog, you get all these amazing extra optical patterns all over the sky. I've never seen anything like this. Someday. And now, how about the white rainbow? Well, they're sometimes called fog bows, which is a really good hint because fog, like mist and clouds, have really, really tiny water droplets. And when water droplets get small enough that they're close to the wavelength of light passing through, another optical phenomenon takes over called diffraction. Diffraction is the slight bending of light around objects, and when there are a bunch of tiny little particles of water in the air, the light diffracts and deviates from its path a bit and spreads out, smears out, the colors overlap, and you get a white rainbow. And finally, what was that rainbow on the grass with all the spider webs that a follower sent me? It said the spiders had gone ham on the lawn, which made me laugh. I initially thought it was the light refracting through the spider webs, but they probably don't have the right shape. I didn't know until I read a little bit more closely that there had been morning dew on the spider webs. And so there were thousands of tiny little substitute raindrops making a beautiful rainbow on the lawn. Amazing.
So really, to explain this, I need to do an experiment. I need to show you what a rainbow actually is. So I have here the sun and a raindrop. Not to scale, I have to say. And so hopefully with these two fine tools, we should be able to demonstrate the physics of rainbows. I need to switch the lights out. Okay, so if you kind of come down to my level. Okay, so if you work your way around towards the right, there's a kind of a little, you can see the little white dot that's sort of reflected off the back of our giant raindrop there.
I can see it.
And as you go around, you'll see that it kind of moves towards the right, so it kind of comes towards you, and then at some point, suddenly it turns colours, so you'll see it go blue, green, red, and then disappear entirely. And the point is you're currently 42 degrees away from the direction that the light's shining in from when you're at that point.
That looks nice, thank you.
Okay, so what we've got is we've got the light coming in, and as you can see, as it passes through this surface, so it goes from one medium to another, the speed of light changes, which has this effect of changing the direction that the light's travelling in. But the amount by which it gets changed depends on the wavelength of the light. Blue light gets bent a little more than red light, so you can see that the blue light reaches the back of the drop at a slightly different point from the red light. And then when they get reflected back again, and again there's another bit of refraction when they come out the raindrop again, and you can see that basically the red light, at least in these extreme rays, ends up travelling at a slightly wider angle than the blue light. That's when as you were panning around, the last light you saw was the red light. So you see just normal reflection pretty much all the way around to here, and then when you're at this last point, where it's the last angle that stuff can actually get through the drop at all, you first see blue light, then you see red light, then you see nothing further out at all. Of course, that's not what happens with a rainbow. With a rainbow, what you have, I'll show you another picture, is of course you have lots and lots of drops, which means there's always one at exactly the right angle to send the red light towards you or to send the blue light towards you. And so actually what you end up seeing is that kind of, remember this magic angle of around 42 degrees. Anything that's around 42 degrees, this angle here between the direction the sun's rays are coming from and the direction you're looking from, you'll end up seeing either red light, or a little bit further out you'll see blue light. That actually means that rainbows actually are round, right? There's a circle of points that are 42 degrees away from these lines of the sun. But what actually happens is that half of that circle is typically below the horizon, so that you see like half a circle of the light, and so you'll end up just seeing the classic kind of rainbow semicircle.
If you have to be at this magic 42-degree angle, how come I can see a rainbow and Johnny Smith 5 miles away can see a rainbow?
Because he's looking at a different set of raindrops. So he's still looking 42 degrees away from the sun, but from where he's standing, he sees a completely different set of raindrops that are all doing exactly the same thing back towards you.
So when I see a rainbow at my house and you see a rainbow over at your house, we're actually seeing two different rainbows.
You're seeing a different set of raindrops that are causing the effect. I mean, obviously it's the same sun that's causing the effect and it's the same physics, but it's a different set of raindrops reflecting it all back to you. And the other thing you noticed is that when you went beyond, so when you were looking kind of closer to the sun, or sort of closer to straight backwards and forwards, so kind of when you're looking at light just reflected off the back of the raindrop, you saw basically white light. And it's only when you get to these extreme angles that you actually see the red and the blue light. And of course that's why if you look at a picture of a rainbow, you'll always see that inside the rainbow is always brighter than outside the rainbow, because inside the rainbow you're seeing just mostly that whitish light being reflected back. It's the sum of all the different colours being reflected back to you, so you see it as white light. Then you reach this edge of it where you're just about seeing just those last few colours, and then when you go to wider angles still, you see nothing at all, and that's why the outside of the rainbow appears darker than the inside of the rainbow.
At the start, I thought you were holding out the promise of something about double rainbows.
Double rainbows we can do too. So double rainbows, also again classically understood, going back at least to as far as, so Descartes did this experiment again in the 17th century. Lots of people have had a go at this. And what they realised is, so if we go back to our original picture for just a second, so what was happening here is the light comes in, gets refracted once off the back of the raindrop, comes back out, refracted again. In a double rainbow, what happens is the light takes a slightly different path. Another picture, you can have the light coming in, gets refracted, gets reflected once, reflected twice, and then comes back out again and comes out at a different angle from if it had just undergone a single reflection at the back. This is another way of making a rainbow at a different angle. So the first way still works. You can have the light coming in and getting reflected once, and that'll give us a rainbow at one angle, or it can go in, get reflected twice, and then we end up with a rainbow at two angles. So you end up with a picture like this. So we've still got the first rainbow here where the light's coming in, getting reflected back to us just once off the back of the raindrop. And so we see the colours spread blue to red, but there's a second way that it can happen, that it can actually bounce twice around the raindrop and take this rather more complicated path. And what you can see is that actually the rainbow ends up being reversed because of that second reflection, where the red light was originally on the outside. If you look at a second rainbow, you'll see that actually the colour is inverted, that the original rainbow, the inner rainbow, goes from blue to red, the second rainbow goes from red to blue. And in fact all the effects are reversed. So as we were talking about before, you see a brighter light down here, then you see a normal rainbow. For the other rainbow, everything's reversed, so you see the second rainbow, and then you see brighter light further away. And so famously you see this thing called Alexander's band, which is the dark region in between where there's no white light gets reflected at all, because in the first rainbow it's all ending up down here, and from the second rainbow it's all ending up there.
It seems to me we should see a double rainbow every time, and yet we only occasionally see a double rainbow.
It really is because so what happens is that in the raindrop, most of the light just goes straight through, only a little bit of it gets reflected. And so actually it's a very inefficient process. Most of the light just travels straight through the raindrop, a little bit of it gets reflected. Of course, if you want to reflect it twice, that means a little bit gets reflected and then only a little bit of the little bit gets reflected. And so the second rainbow is always much fainter than the first. So it is actually always there, and in fact very occasionally you can even see a third rainbow which is even fainter still. So these other rainbows are always still there, but they're always much fainter. So if you can only just see the primary rainbow, you're not going to see the secondary rainbow at all. And it's always when you have a really stonkingly bright primary rainbow that you end up seeing the secondary one. People often ask this question, you know, don't you lose the magic of something by actually understanding it? You know, by actually understanding where a rainbow comes from, isn't it not beautiful anymore because suddenly you've explained it and it's all very simple and trivial? And of course it doesn't, right? I mean, you know, I understand the physics of rainbows, but I can still go out and look at one and say, wow, that's pretty. So it really, you know, it doesn't have that negative effect at all. It just adds to the experience of seeing a rainbow. That not only does it look beautiful, but you actually understand why it looks beautiful too.
You can get some absolutely wonderful optical phenomena, and I've certainly seen the one that they showed from the aeroplane looking out onto the clouds, the glories. Yeah, you can readily get that if you know to actually look in that direction. Now to close, we'll look at the eruption of Kilauea, which was just a couple of weeks ago, and the Hawaiian island is shown down there in the bottom left. And you can see the size of these volcanoes is tens of kilometres, so really, really large overall. And as you can see there are the 5 main volcanoes that form the main island of Hawaii. On the video that shows in a moment, you'll actually seeing the eruption in real time, and it's 9 hours behind universal time, so we're currently 10 hours ahead of universal time ourselves, but Hawaii is 9 hours behind. And before we do, just to give you an idea of the scale, that's a daytime image of the centre of the crater. And can you actually spot the survey helicopter that's towing an antenna across that image? Gives you an idea of the scale of things. Can you make it out? Anyone see it? By the smoke, you reckon? Okay, let me give you a bit of a clue. Now that gives you an idea of the size of it, and now we'll go into it. US Geological Survey has the Hawaiian Volcano Observatory that has live webcams, so you can actually go on and actually see the status of the eruption at any time. And I believe Kilauea is the second most active volcano on the planet. So it has erupted before and has a potential of erupting really, really largely in the future. Okay, so that's it for June's meeting, and we'll hopefully see you next month at July's meeting. Thanks for coming.